Next up is Alessia Romani. Alessia got her PhD in design at Politecnico di Milano and is a postdoctoral researcher at the Free Appropriate Sustainable Technology FAST Lab at Western University. Her research explores the interconnections between designs, materials, 3D printing, and sustainability, bridging design and engineering through open source technologies and materials. She will be joining us virtually for her talk, Addressing Replication Challenges in Distributed Assistive Technology, Insights from the Development of Open Source 3D Printed Crutches.
Hello everyone, I'm Alessia Romani, and today I will speak about one of the works connected with open source assistive technology from FastLab. The title is Addressing Replication Challenges in Distributed Assistive Technology, Insights from the Development of Open Source 3D Printed Crutches. Just quick words about my work. I'm Alessia Romani, and I am a postdoctoral researcher at FastLab, the Free Appropriate Sustainable Technology Research Group in the Faculty of Engineering at Western University. My background is mostly related to product design and engineering design, and I gained some expertise in materials engineering and additive manufacturing during my research path. Before joining FastLab, I studied and worked in Italy at Politecnico di Milano. Here, I worked as a research fellow at the chemical department and conducted my PhD research at the design department, gaining expertise at the intersection between design and material for sustainability. That's why my research interests are mostly connected to the intersection between design and engineering for sustainability, thanks to the use of materials and digital fabrication tools such as 3D printing. I'm currently working at FastLab, the Free Appropriate Sustainable Technology Research Group at Western University at the Faculty of Engineering, led by Dr. Joshua Pierce. Here, I'm working as part of an interdisciplinary team made up of different research and professional figures, such as engineers, designers, scientists, and makers. And we are working together to foster sustainability and enable it thanks to technology. But how are we making it possible? In our case, open source is the way. So we are pushing open and appropriate technologies and trying to make it free and accessible to everyone, fostering sustainability at different levels. We are currently involved in projects mostly connected with two main research streams. The first one is distributed recycling and additive manufacturing, which is also my core topic at FastLab. And the second one is focused on enabling sustainable energy and technologies, such as photovoltaics. In both cases, our focus is to achieve sustainable development goals thanks to accessible technologies, aiming to foster sustainability in real-life context. At FastLab, my activities focus on applying open design principles to physical products and studying sustainable materials for accessible product application. All of this thanks to digital fabrication. You can find us in the Thompson Engineering Building at Western University as part of the Faculty of Engineering, and we are in the main campus in the city of London, Ontario, in Canada. If you want to know more about our work, you can also check our Appropedia page with our projects here. Today, I'm going to focus on a specific project connected to the topics of this conference and open source healthcare. First, I will speak about the replicability of open source assistive technology. I will then focus on a case study that we are working on and connected to distributed open source assistive technology products. I will also share some insights from the ongoing development and validation of this project, followed by some key aspects connected to replicability and future work on the projects as well. Let's start from the replicability of open source assistive technology. But what is replicability in the open hardware context? A possible definition could be the one provided by Omer and colleagues. So replicability is, in this context, the ability of an individual builder to construct a functional hardware version in their respective settings. And this means that the replication should be tailored to users who are prosumers in this case, and local communities as well. And all this process should be supported by open documentation of the designs. Replicability can be achieved thanks to distributed manufacturing because processes such as open source 3D printing allow for more accessible, affordable, and customizable solutions. They can also be available in low resource or humanitarian contexts, for example, having access to a low-cost 3D printer or locally available materials. And all these technologies and materials can support open source local production partners, producing what is needed and only if needed. Replicability is also fostered by open design principles. Project and documentation for open source products should be available to all users. Those products should also be replicable by using accessible equipment and tools available to users. Finally, the replication of these products should be always possible, together with the adaptation or modification according to the specific needs. So the question is mostly if this is enough to ensure real-world adoption. And I would say no, because open source hardware and products should also consider other factors when reaching users and real-world context. For example, easy replicability, quality assessment, or affordable fabrication, and not only the use of open design principles. And here is another big question. So what is replicability when applied to the open healthcare context? This definition might be trickier to define than the previous one. So there are different aspects we should consider for that. The point is not only achieving function and hardware version in their respective settings, but also avoiding adverse side effects during their use. This can be done thanks to the validation and testing of the device and its replicas. We should also meet satisfactory replication despite the variability embedded in distributed open source products, such as modifications in their design, variability in local materials, and manufacturing processes. This last part is also still a topic for real-world adoption of open source assistive devices, and that is also part of what this presentation is focusing on today. So today's aim is to reflect on the replicability challenges existing in distributed open source assistive technology, and I will do this through an ongoing case study from our lab. This project focuses on the development and validation of a version of 3D printed forearm crutches founded by the Interdisciplinary Development Initiative at Western University. Our lab is currently working together with other departments and groups at Western, merging each collaborator's expertise and knowledge to foster the real-world application of such an open-source assistive product. I really want to thank them for all the participation and engagement they are showing in this project. What we are aiming for is to develop an open source 2-pieces 3D printed crutches that should be replicable in low resource settings and in humanitarian context. And for this reason, we aim to achieve some replicability goals. So the first one is optimizing the fabrication of this product on low-cost desktop side 3D printers to reach a broader audience of customers. The second one is to reduce the need for off-the-shelf parts and make this product less influenced by the availability of such components. The third one is trying to rely on locally available materials, or even better, if possible, discarded parts for non-structural part of the product. Finally, we aim to meet the standard load-bearing requirements for safe use of standard crutches, paying attention to safety when the user is using this device. The development workflow can be divided into different steps. We designed the first version of the crutches during the first design phase, and we optimized its fabrication as a second step, reducing time and material use. We then tried to study the replicability of these parts by considering different materials and 3D printing setups. We assessed all these different combinations through mechanical tests, which were useful to improve and further modify the design, make it safer and suitable for use. Now we are trying to replicate the mechanical test on this new version, keeping the different combinations of materials and setups. And at the same time, we are working on alternatives to some less available materials or more affordable options. Focusing more on the development and validation of the crutches, we are working on a version that is made of a 2-piece 3D printed forearm upper element, this to facilitate the replication of the 3D printed components with low-cost 3D printers. The assembly can be divided into different components using 3D printing for most of the parts, either with rigid or soft materials, and only a few extra off-the-shelf components. We included parts made of veggie and TPU filaments for rigid and soft parts of the product, and then we selected wooden dowels as the main connection parts, allowing for customizable lengths, and we added wood screws for the assembly, the off-the-shelf part included in this product. All the 3D printable parts fit the volume dimension of desktop-size 3D printers, making the replication easier for users with small format 3D printers and, at the same time, allowing for multiple part 3D printing if using large format systems. The second step was then optimizing the 3D printing settings. So what we did was print full solid parts made of PETG to ensure the mechanical requirements we needed for safe use of the crutches. We also considered other aspects during the previous phase, which we checked when printing. First, we avoided the use of supports thanks to the designed shape and selected building orientation. And we also tried to suggest a preferred building orientation through the design shape of the 3D printed component. For instance, specific flat base areas or similar aspects, adding a further way to control replicability and guiding the user. On the one hand, this was also useful to reduce the time used for printing the different parts, the material used, and the waste. On the other hand, these choices make the part easier to fabricate by non-expert users. Then we tried also to work more on the replication aspect connected to the 3D printed parts, and we considered using different materials, filament and qualities, and also different 3D printed formats. What we did was select one material for the structural components, PETG in our case, and print them with both virgin matte filaments and recycled ones. We did this either with small-sized 3D printers, such as Prusa and K3S, and large format 3D printers with building plates suitable for printing multiple parts at the same time. These trials resulted in 4 different batches of samples, where batch number 1 uses virgin filament and small-scale 3D printers, batch number 2 switches to recycled PETG, and the other 2 batches are focusing on large format 3D printer, where batch 3 uses virgin filaments and batch number 4 goes back to recycled ones. These parts also correspond to 4 batches of assembled crutches that we assembled to refine the assembly procedure and perform mechanical tests on this version. We first referred to the right standard for the test, and we selected the ISO standard available for working products to be used with one arm. We then used a custom setup to simulate the anatomical structure and movement of the arm. This setup was previously developed by our lab in another publication, and we adapted it for our current configuration of the crutches, replicating the natural posture during use, thanks to simulated joints of the forearm. We then started to test the applied and increasing load, as you can see from the video. And we did it for each of the 4 batches of samples that we have, which means 5 crutches each. So we tested around 20 prototypes in total, trying to reach the maximum load. And doing this, we also analyzed the maximum load achieved by the different materials and 3D printer combinations and the failure types, which were quite different for each batch, but should ideally meet the standard. So we aim to support 100 kilo without failing for 10 seconds to meet the standard. These results allow us to make further modifications, which first means modifying and redesigning the critical components leading to failures, in our case, the handle, to achieve the target standard, so 100 kilo without failing for 10 seconds. We then reprinted the new parts and further tuned the parameters to reduce any inconsistency in the material flow and ensure 100% solid parts. And finally, we reprinted the parts with virgin and recycled materials using both small and large format 3D printers according to the previous batches. We are now doing the mechanical tests on these new prototypes, and they look promising because we are getting to the standard requirements for safety, and the replicability of our part is good because we are observing similar failure modes on the sample, and these also highlight some patterns and supporting replicability. We are also working on how to replicate this product in local low resource settings by providing alternatives and redefining our current design. For instance, some ongoing tests aim to avoid the use of TPU filaments, which can be tricky to find in some contexts. And for this reason, we are also considering already available materials or discarded parts for non-structural elements. For instance, we are trying to develop one version using discarded bike tires for the padding and grips, also simplifying the 3D printing process for non-expert users. As far as now, these ongoing activities have led to an important takeaway about the replication challenges behind open source 3D printed crutches. Such challenges should be considered during the whole design process of the crutches. And for doing this, we should find new ways to assess the variability connected to their distributed application and simulate them during the design process. This concept can also be extended to the open source healthcare context, leading to the main takeaways of this presentation. And according to this, distributed open source assistive technology needs to include replication assessment during the design process, considering potential variability connected to the replication context of the product. This means that we need to design and share specific procedures and methodologies to be included in their development. Of course, replicability is also affected by different factors. Study from our lab highlights some key aspects that can be seen as a starting point for structured replicability assessment in the context of open healthcare products. Considering materials and technologies, we should consider the local availability and affordability of materials and parts, and the same should be done when choosing manufacturing technologies. In general, the target is an adequate quality level of materials, parts, and technologies to ensure both functionality and, most of all, safety and no side effects during use. Focusing on designing replicable products, we should rely on available and affordable materials, parts, and technologies as much as possible, designing and keeping in mind possible alternatives without affecting the main function and safety. The extent to which products are designed to be easily replicated guides the whole design process and should consider non-expert user as the main target for replication. This approach can help increase the overall quality of replicas by simplifying their replicability. Back to the crutches, our next steps will be to conduct user tests, creating detailed replication guidelines to be released, and to support the replication of the crutches in a real-world local context. Finally, additional factors affecting the replicability of distributed assistive technology should be detected and studied in future projects, including how to assess them during product development. So, what can we do to address replication challenges in distributed assistive technologies? I would say this is an open-ended question that we should address altogether. So, thank you for your attention, and thanks to the collaborators involved in this project and the participant organizers of this event. Feel free to follow us and connect if you're interested in our work.